Hello, and welcome to the Organic Optoelectronics Research Group in the Department of Materials Science and Engineering at the University of Toronto. My name is Michael Helander, and today I'm going to be talking about some of the research that goes on here in our group. So the type of devices that we work on are particularly light-emitting diodes. So for example, things like this. So this is a small light-emitting diode. This is something that we're very familiar with now in everyday life. It's used, to make the indicators on our keyboards and for our cell phones, and small little blinking lights for various indicators. And so these are made from inorganic compounds. They're small, they're inefficient, and they're kind of limited to this small form factor like this. So what we're interested in doing is making these LEDs out of organic compounds. And when I talk about organic compounds, we don't mean organic farming, not fruits and vegetables you find in your supermarket. What we mean is things from organic chemistry. So molecules made from carbon, nitrogen, oxygen, and hydrogen. So things like this. So this is a molecule that we find in everyday life that a lot of us are probably very familiar with. This is caffeine, something that is in our coffee, our soft drinks that a lot of us probably had for breakfast this morning. And so we don't actually use caffeine in our research, but we use other molecules like this. This is called copper phthalocyanine, and this is something that we're all also very familiar with, and a lot of people are probably wearing this on a day-to-day basis. So this is a pigment. It's a blue dye that's used to dye blue jeans blue and to dye other dark navy clothing dark navy. And so this is nothing more than really just a pigment, a powder, and if we just look at a little bit of this on a white sheet of paper, we can see that this is just made up of organic powder, and it's blue. Used to dye blue jeans. What's interesting about it is its structure that makes it such a good dye and pigment. All these kind of ring-like carbon-carbon bonds in here also make this molecule very good at conducting electricity, which means that we can start now to think about actually using electricity to stimulate these molecules to do various things, such as emit light. And so as I mentioned, a lot of these dyes, and pigments that we find in everyday life that make our clothing all different bright colors, are nothing other than simple organic small molecules. So different colors like this. And what's interesting is that we can get colors, any color of the rainbow out of these. And a lot of these different organic compounds and dyes have the interesting property that they're very fluorescent. So they look kind of interesting colors. If we shine an ultraviolet light on them, they start to glow. And so what we're actually seeing here is that the ultraviolet light is stimulating these different organic compounds to emit light of different colors, whether it be red, green, blue, orange, pink, purple. Pretty much any color of the rainbow we can think of. And so we're not interested, obviously, in shining light on these different molecules and getting different color light back. What we're interested in doing is applying electricity to these molecules in order to get light out, in order to make these LEDs type structures. And so the way we do that is we take these compounds, and again, they come to us as simply just powders. And we want to then take these powders and process them into very thin films. So very, very thin layers. And when we talk about thin films, we mean something on the order of 100 nanometers thick. So this is, 1,000 times or more thinner than a human hair. And the way we do that is using the type of processing equipment behind me, which is a high vacuum deposition system. And so all that this fancy, shiny equipment does is basically take this powder and process it into that very thin layer. And we can coat that thin layer onto various substrates. And when we say substrates, what we pretty much mean is anything. So it can be a piece of glass, a piece of flexible plastic, even a piece of paper. And then by applying some simple electrical contacts, we can now hope to actually stimulate these molecules using electricity. And so here's just, for example, a simple device we've made up in the system behind me. So this is on flexible plastic. I've coated some of these different fluorescent dye molecules on here. And now when I apply electricity through a small just battery or power supply, these molecules are getting stimulated and they start to emit light. And so we can see this is emitting green light. And this is flexible, paper thin. So now some of the really exciting applications of this technology really start to become apparent. So this is a device based on simply green molecules. But we have compounds that can emit red light, that can emit green light, can emit blue light, RGB. So when we can combine these different colors together, that gives us the foundation to make a full color display. So we can imagine we can now start patterning each of these little pixels, one red, one green, one blue next to each other, make them smaller and smaller, and now we can have a paper-thin display. It's made on plastic that's now flexible. So you can imagine that your next 55-inch TV is not going to be this thick, rigid thing you hang up on your wall. It's going to be nothing other than a thin sheet of plastic that you can roll up and take with you at the end of the day. So hopefully this is giving you a little bit of insight into some of the exciting applications that we'll see coming onto market in the near future, and some of the exciting research that's going on right here in the Department of Materials Science and Engineering at the University of Toronto. Thank you.